Here's problem 516. In the figure shown, the coefficient of kinetic friction between the block and the incline is 0.4. What is the magnitude of the acceleration of the suspended block as it falls? Disregard any pulley mass or friction in the pulley. You know, the two blocks are connected, so if the suspended mass is falling with some value of acceleration, the mass that's on the incline will also have the same value of acceleration because they're connected, and so they will kinetically move with the same values. Let's visualize what's going on here. We've got mass 1 here, which has a mass of 2m. m wasn't given, but we do have a mass 2, which has a value of mass m. And we're on a 40-degree incline. Now, if we were to visualize the kinds of forces that are going on here, we would have weight here at the mass 1 equal to m1g, and mass 2, for that matter, would have weight as well, which we would break up into two components. We would have one component of weight, m2g sine theta, down this incline, and then we'd have another component, m2g cosine theta, into the incline. We also would have a normal force that would offset the m2g cosine theta so that there was no net force in what we might consider the y direction on this incline, x direction being up. Alright, well, there is friction on the incline, and it looks like the 2m is a bigger mass than the m, so it's very likely that this system is going to move toward the left. In other words, the little m, mass 2, is going to move up the incline. So friction is going to work against that motion, and hence we'll have a force of friction, let's call it F2, which will be equal to mu times n, the normal force, whatever that is. Now, so these are the forces that are acting on this system. Let's kind of blob this whole thing together and think about this as one system. We got tension on these two as well, and if we blob them together, we don't have to worry about the internal tension because that's part of the blob. That's internal, so we just have to worry about these other external forces. And also, the normal force and this m2g cosine theta are transverse to the axial motion. The axial motion is going to be one acceleration in a forward direction like this. But we do want to find the normal force, and so if we looked in the y direction on the incline, summation of those forces should equal 0, and that would be equal to the normal force minus m2g cosine theta. So the normal force will equal m2g cosine theta is 40 degrees, so that's going to be the cosine of 40 degrees. And that's going to be equal to, well, we don't know, so m2 is just m, and this would be times 9.8 times the cosine of 40 degrees. So what is that? 9.8 times cosine of 40 is 7.51, so 7.51 m. We wish we knew what m was, but we weren't given that. So that's our normal force. Our frictional force then is mu times the normal force, and that would be 0.4 times the 7.51 m. And so that will be 3.00, that's nice, 3.00 m. Alright, so that's our frictional force. And now if we were to write Newton's second law for the positive acceleration direction, the forward direction being positive, we've got this m1g making it go right at the start. So we'll have the summation of all the forces in the positive direction will be our total mass times acceleration, and that's going to be equal to m1g, and then we have a m2g sine theta at the pulling back on it, So that's going to be minus m2g sine 40 degrees, and then minus friction. We're only concerned with the acceleration either in the positive or negative direction of the acceleration. So this sets up our Newton's second law for that. Our total mass is going to be m1 plus m2, so we got m1 plus m2 times acceleration is equal to m1g minus m2g times the sine of 40 degrees minus 3 times m, big M. Let's go to the next page. So we have mass 1, which is 2m, plus mass 2, which is m, times acceleration is equal to m1, which is 2m, times g, minus m times g, sine 40, minus 3m. We have 3ma is equal to m times 2g minus g sine 40 minus 3. M's cancel out, so that was a nice thing because we weren't given the mass. And now we have acceleration is equal to 2 times 9.8 minus 9.8 sine 40 minus 3 over 3. If I figure this out, we have 2 times 9.8 minus 9.8 times sine 40 minus 3 divided by 3. I get an acceleration of 3.43 meters per second squared. So that is our acceleration. Since we came up with a positive value, our assumed acceleration for this blob was correct. That was the positive direction. If we had come up with a negative value for this total mass of 3m, then we would have just had assumed the wrong direction for the acceleration to begin with. But we would have gotten the same magnitude of acceleration. So our answer is 3.43 meters per second squared.